Probably maybe there's one small
Live? Okay. All right. Yeah, feel free to come to the seats at the front if you're standing. Right, let's get started. Good evening. It's so great to see a packed house at 5:30 p.m. My name is Venkat Guruswamy, and as director of the Simons Institute for the Theory of Computing, it is my great pleasure to welcome you all to today's Theoretically Speaking public lecture titled AI's Model of the World and Ours by John Kleinberg. A bit of introduction about the Simons Institute. We are the leading international venue for collaborative research in theoretical computer science. Established in 2012 with a generous grant from the Simons Foundation, the Institute brings together the world's foremost researchers, as well as the next generation of outstanding young scholars, for sustained collaborations on thematic programs that span not only the foundations of computing, but also its interface with the sciences, mathematics, technology, and society. Alongside our research mission, we seek to foster public understanding of algorithmic science and its ever-expanding influence on our lives through communication, outreach, and events such as this one. In that spirit, today's lecture is part of our Theoretically Speaking series, which aims to highlight exciting advances in the theory of computing for a broad audience. And if you're active on social media, we invite you to live post this event. You can use the hashtag #SimonsLive and tag us at Simons Institute. So if others are interested, they can find and follow the conversation. And before I introduce today's distinguished speaker, I would like to acknowledge the generous support of the Simons Foundation and Simons Foundation International, as well as our industry partners and individual donors, which makes our research mission and events such as this one possible. With that, it is now my honor to introduce today's speaker and one of my personal academic heroes, John Kleinberg. John Kleinberg is the Tisch University professor in the departments of computer science and information science at Cornell University. John's work has shaped multiple areas across computer science, from algorithms and networks to the ways they interact with large-scale social and information systems. His research has illuminated how technology-mediated systems function, for example, how information propagates, how networks evolve, how algorithms make decisions, and relevant to today's talk, how AI models represent their knowledge, and so on. His work is characterized by a remarkable ability to distill complex real-world computational phenomena into crisp theoretical questions. And his models have a knack of capturing the essence of these phenomena with just the right abstraction, yielding insights which are both mathematically profound and at the same time deeply relevant to how modern information systems shape our world. His writing reflects the same clarity. John is the co-author of two highly influential textbooks, Networks, Crowds, and Markets, which helped lay the foundation of network science for a broad scientific audience, and the widely used algorithms textbook, Algorithm Design, which has shaped how generations of students learn to think algorithmically. Now, as for John's awards and honors, if I list them, we'll be here well past dinner time. So just a small sample, I will mention the MacArthur Fellowship, the Nevelina Prize, which is now called the Abacus Medal, the ACM Prize in Computing, the World Laureates Association Prize, and election to both the National Academies of Science and Engineering. John is one of theoretical computer science's greatest ambassadors, and it's our pleasure to host him again in this public lecture series. So please join me in welcoming Professor John Kleinberg to Simons Institute's Theoretical Speaking.
All right. Yeah, thanks,
thanks very much for the invitation to come speak here. And thanks all of you for turning out at this evening hour. It's always a pleasure to come speak at the Simons Institute. And it really has, just as someone who is a frequent visitor to it, just been really a sort of a hub of activity and sort of an intellectual beacon for the theoretical computer science community, both for all of its, I think, internal activities, all of the kind of theory-focused activities that have gone on here, as well as its outreach to both into the sciences and academia more broadly, and also to industry and civil society. I think it's really, it's been a great resource, which we're really grateful for all the effort that people here at Berkeley have put into it, as well as, of course, to the Simons Foundation. It hosts events like this, which bring us all together. So I wanted to talk about some things that a group of us have been thinking about with regard to AI and how it interacts with the world. This is going to be joint work with a whole set of people listed here, and I'll try to kind of introduce them gradually as we grow through things. I guess for sort of thinking about this topic, it's useful to go back some distance and think about, how did we get here? And so let's start with the internet, which all of this is built on. What's interesting, of course, about the internet, we're now sort of in the maybe 30th or so year of the sort of widespread public use of the internet, somewhere between 30 and 35 years, depending how you count. And one thing that's been interesting in that period is the way in which the metaphors that we've used for the internet have evolved over time, right? So if you go all the way back to 1993, 94, when the first graphical web browsers came out, if you had asked me in grad school at that point, or other people, how do you think about the World Wide Web or the internet? I think we would have used this metaphor of the library, right? It's a vast universal library of all human knowledge. We put the knowledge online and we've linked it together, and and that sort of would have been how we thought about it. And that metaphor, I think, worked pretty well for guiding how we approached things on the internet for, a good 10 years. But then there was this really formative period, 2004, 2006, when people sort of stepped out from behind their web pages and began interacting more directly. They began, uploading photos much more actively. They posted and commented on what we eventually called social media. They tagged people in images. And so this metaphor of the crowd began to kind of merge with the metaphor of the library. Right? 2004, 2006, right, was sort of such a compressed window that was in sort of a 3-year period, the creation of Facebook, YouTube, Twitter, the iPhone, right, all of that in this really formative 2004, 2006 period. And that went on for a while. And I think actually for a while people said, okay, this was the answer. This was what the web was all about. It was really about unlocking human capability. Because in some sense, you can think about computing as always involved in this very slow pendulum swing between two views of what computing is, right? Computing is either sort of, a enabler of human capabilities, or it's a means of automating things so that they can, be done without humans present. And that pendulum swings back and forth on a very long time scale. And in 2004, 2006, we're like, yes, the web was really all about unlocking human capability, which it assuredly is. But there was one more twist of the pendulum, which was in 2012, 2014, again, a really rapid 3-year period of enormous advances. The power of deep neural nets combined with huge data sets suddenly caused us to really achieve massive performance improvements, many of which occurred, here at Berkeley and in the Bay Area more generally, on 50-year-old problems in the field, right? Recognizing the object in an image, turning a sound signal into transcribed text so as to do speech recognition, summarizing documents written in natural language. Right? All of these problems that the field had very much wanted to solve, we're suddenly seeing these enormous performance improvements. And in a way, it was partly, to a large extent, there were computational advances, but there was also the fact that all that data people had been putting online, all those photos people had uploaded, were the training data for these algorithms, right? A bunch of things that we had wanted to do in the 80s and couldn't do, the people doing them, trying to do them in the 80s, assured us that if only they had 100 billion labeled images instead of 10,000, right? If only they had maybe 7 orders of magnitude more data, this stuff would really all start working. And in the 1980s, how are you supposed to audit a claim like that? I have no idea. But roughly speaking, that's what happened, right? The field took this 20-year-long detour. Crowds entered the internet, tagged photos. They said, this is my friend, this is a car, this is a tree. And 100 billion images later, a bunch of things started working in ways that they simply hadn't before. So that's actually, for those of you keeping score at home, if you really believe these things move in 10-year increments, we're kind of at the end of yet another 10-year increment. So you can ask yourself, you can ponder, is there some fourth thing, or maybe this third thing is the last thing we're ever going to have? Who knows? So algorithms AI have become powerful because of these two reasons: massive computational resources and this massive amounts of data that we have all collectively put online. And so it causes us to really ask the question, when an algorithm looks out at all of that, what is it actually seeing? Right? How does an algorithm see the world? And there's a lot of metaphors that go on here. I often do find it useful to think of, the algorithm is in some sense this hyper-intelligent alien that can analyze enormous amounts of data, do enormous amounts of computation, but it does not really live in the world. It does not, it observes the world, and it tries to figure out things about the world by looking at this data. And I realized when I sort of began to ponder these metaphors, and I think I probably began pondering them as all this data came online circa 2004, 2006, that I'd actually sort of heard this thought experiment before, but not in a computer science context. Rather, when I was an undergrad at Cornell, one of Cornell's big exports to the world at the time was Carl Sagan, the famous astronomer and one of the 20th century's most notable popularizers of science for the general public. And Carl Sagan sightings on campus were quite rare because he was often traveling around doing the kind of Carl Sagan-like things that he did. And so when he gave a lecture on campus, people showed up for it. And so in spring of 1993, he gave this talk with the title, "Is There Life on Earth?" Kind of a strange title. Based on a paper he had published in Nature with the only slightly less strange title, "A Search for Life on Earth from the Galileo Spacecraft." Now, it turns out Carl Sagan had been asking this kind of question, is there life on Earth, for his whole career. You can find papers by him in the 60s about this, in the 70s about this. What did he mean by this? Well, so he was often sort of organizing these joint Cornell JPL missions to the outer solar system, looking for evidence that there was, maybe once life on the moons of Jupiter or Saturn, right? Maybe once Titan or Europa actually had life on it. And so they would fly these space probes out there. And in this case, they were flying the Galileo spacecraft out to kind of do these measurements to try to detect weak signals of life or maybe there was once life on these moons. And the way these missions go is you fire this thing, you have to get enough speed to go to the outer solar system. So you fire it toward the sun, and it slingshots around Mercury, picks up speed, and goes to the outer solar system. Which means that at some point, it's passing back over the Earth on its way out toward Jupiter and Saturn. And so Carl Sagan asked the question, if we're going to try to detect life on the moons of Saturn and Jupiter, or faint traces, probably as a dry run, just as a good double check on our instruments, we should be able to detect the presence of life on Earth. Like, if we can't do that, probably this mission does not have a really big chance of succeeding. And so in his lecture, he used the metaphor of aliens, right? Because just as algorithms looking at the world are like aliens picking up the data, his Galileo spacecraft was at that point essentially like an alien space probe looking down at the Earth, picking up physical and chemical measurements, trying to figure out, can it detect life? Right? So he asked, if we were aliens and we had this data, would we recognize something anomalous about the Earth that might tell us there was life? Now, his questions were sort of physical and chemical and not germane to this talk. For those of you who are curious, certainly one of the notable things about Earth is that there's an enormous supply of diatomic oxygen existing right next to flammable gases like methane, which should not happen, right? That should all combust and just be gone and become water and carbon dioxide. The fact that it's there suggests something very complicated is replenishing diatomic oxygen into the atmosphere. That was certainly one of his big tells. Anyway, so let's think about this life on Earth question. So around the birth of social media, a group of us, Lars Backstrom, Dave Crandall, Dan Huttenlocher, and I, began to try our own life on Earth experiments with some of the early social media sites, circa 2004, 2005. And one way to do this is to go back to some of the early photo sharing sites, right, when photo uploading and photo tagging was first a thing, and look at how they were displayed on the Earth, right? So you could take, for example, a black screen here, and you could go to a 2005 era social media site where people were first uploading photos, and take the latitude, longitude of every photo that was uploaded, and just put a white dot on the screen. Okay, so just a big pattern of dots where every photo was uploaded. And when you do that, you get a shape that looks like this, right? And of course, the fact that you see a map there is only in your mind. It's really just a pattern of dots. But it is certainly true that people take photos up to the edge of the water, and many fewer of them take photos after that. Similarly, you see these particularly bright spots at like cities of the world. You see long strings where there are rivers, interior seas. You see a bunch of things. Now, we begin to notice a few things. Obviously, first, I'm only showing about 40% of the Earth's area here. I'm not showing the whole Earth. But also, this is not, obviously, this is not the population density of the Earth. There are incredibly densely populated areas here, here, there, that simply were not on this particular social media site in 2005. They weren't using it. So this, and this, of course, is, something that we see, whenever anyone talks about biases in the training data, this is certainly a key example of bias in training data, right? This is not the Earth. This is the 2005 era photo uploading portion of the Earth, right? And even the parts that are heavily covered, like this is not the population density of the Himalayas. This is all the people who went and climbed the Himalayas and later uploaded their photos to social media. And of course, there are also artifacts in the data, right? So if I were to extend this picture just a little bit south here, kind of right here, there'd be a really bright dot, like all these bright white dots. A really bright dot kind of in the Atlantic, in the curve of Africa there, kind of south of Accra, west of Libreville. And you look at that and you say, I wonder what that is, right? And the answer, if you've played with geodata, is that there are a lot of phones, certainly in 2005 there were all more phones, that when you uploaded it, they didn't report their lat long. Instead, they reported 0,0. And where is 0,0? It's where the prime meridian intersects the equator, which is right there, right? So you have to notice these things in the data, right? Some of it is actually just kind of anomalous. So this data was like pure signal, right? It was sort of amazing how much you could get out of things like this. You could say, for example, take the 100, or say the 20 densest 100-kilometer circles, and take the textual tag in there that's the most anomalous, right? Not the most frequent. Right, the most frequent might be trip or family or vacation, but the one that deviates the most from its background distribution over the whole world, right? As in, people say trip and family vacation all over the world, but only when they're staying at the base of the Eiffel Tower do they say Eiffel Tower. And then you could take 100-meter disks within each one, the distance at which you can see something and take a photo, and look for the most common word there, right? And then you get these hotspots, right? And so, for example, from this already in 2005, and remember, this entire site had fewer photos than are uploaded in one day of social media now, right? So it was both a huge amount of data and almost nothing by the standards that we're talking about now, right? And so you get the 20 most common, the 20 tags of the densest things here. And for each of them, the 4 densest 100-meter circles within that city, and the names assigned to them, right? And again, almost all of it is, highly meaningful here, right? There's incredible amount of signal compared to the noise. I mean, we could debate whether the Apple Store is truly the 4th most important landmark in Manhattan, but apparently, if you were a user of this social media site in 2005, it was like a pilgrimage to go there, take a photo of it, and upload it and tag it. Right? And so it's sort of a reminder that these 100-meter disks, with the names attached, are sort of hovering over these things. It's sort of like the beginning of every alien invasion movie you've ever seen, where one morning you wake up and the flying saucers are over the Eiffel Tower and the Empire State Building, and the reporter stands there puzzled and says, we don't know what they are, they just showed up this morning. And you wonder, how did they know to hover over all those famous landmarks? And maybe for the aliens, it's not as hard as we think it is. So the point is, this is the data that we're building on. And one of the key things about computing is the extent to which it works based on abstraction barriers. Right? I think this is one of the sort of really powerful theoretical constructs that goes back to the very early days of computing, that if you can find the right abstraction barrier, then you can separate the sort of low-level implementation of the technology, and all your reasoning about that, from the applications that you build on top of the technology. Right? And so on the one hand, and so often people think of this as like the metaphor of the hourglass. Right? There's a lower lobe of the hourglass where we sort of build all this sort of conceptual infrastructure for how to create these algorithms. And then there's the upper part of the hourglass where we build on top of that technology. And as long as the two parts agree on a consistent model, right? So, a consistent model of the shared memory computer, the Turing machine, the Boolean circuit, the distributed system, right? These are kind of constructs that we create so that the people working down here can communicate with people up there by exchanging very, very little information. Right? If you know that you're building a chip that implements the shared memory computer abstraction, then someone writing a high-level programming language or programming in it can program to that high-level abstraction, and they'll meet in the middle. Okay, and so this is the substrate on which many of these AI applications are being built, right? Huge amounts of data and machine learning algorithms down here, these AI applications up here communicating through this very thin interface in the middle. Now, that brings us to the present, to super powerful AI. And obviously there's a lot of, concern, interest, fascination, all of these emotions about what these things are capable of. And you see discussions of, if AI were to become superhuman in domain X, what would that look like, right? So what would it look like if we had superhuman AI doing mathematics, or making legal arguments, or making medical judgments, or composing music, and so forth? And these discussions are, on the one hand, fascinating. On the other hand, they turn immediately speculative. We don't really know what's going to happen if we're in those situations. It's certainly wise to sort of think ahead and be prepared. But if we really want to think ahead, then there's something else we could also be doing, which is to look for a domain where this has already happened, right? Where we don't have to guess what would happen in a world of superhuman AI, but where we simply have it. Now, we want to choose our domain carefully, right? I think like adding up long columns of numbers is a domain in which computers were superhuman for a long time, but it doesn't fascinate us because we never thought of adding up long columns of numbers as special to us. So what we really want is some kind of creative pursuit in which algorithms have conclusively surpassed human abilities, and yet, it has the property that people, in this area, it's a sort of aesthetic, human, creative activity. People train their whole lives, achieve this level of mastery that inspires a sense of awe in other human beings, where you can have whole libraries filled with a century or more of scholarship. And yet, despite all of this mastery, this training, this scholarship, despite that, computers have simply surpassed human beings, right? And arguably, a sort of key example of this is chess, right? Chess is a domain which certainly is a sort of a pinnacle of human creativity, up there with music composition and literature and so forth. And yet, where if the goal is to win chess games, humans have long since been surpassed. Now, lots of people have worked on chess as a model system, right? Newell and Simon worked on chess. Claude Shannon, pictured here, giving a prize to the creator of Deep Blue, worked on chess. Deep Blue famously defeated Garry Kasparov, the world champion, in 1997, which was sort of a moon landing type event for it. In some sense, like chess has long been a model system for decision making. It's one of the few things to have been metaphorically called the Drosophila of more than one area, right? The Drosophila, the fruit fly, the organism that's so malleable that it can be the model system for genetics. And metaphorically, right, chess has been called the Drosophila of psychology by Herb Simon and William Chase, the Drosophila of AI by John McCarthy. But now it's sort of the Drosophila of one extra thing, which is of superhuman AI. So knowledge of chess will not be necessary for this talk. You can just think of it as a human activity where there's a lot of, just a lot of human mastery that's occurred over the past century. But just as a brief timeline, computers just kept getting better and better at chess. And the late 80s, early 90s were this interesting period, which sort of eerily evokes some of the things that you hear now, where they began defeating human grandmasters, right? They were now beating all but the best 100 people in the world. And people sort of were still skeptical. 1992, 93, they're like, yeah, I see that happening, but I think there's something special about the best few human beings, that they're just not going to get defeated by computers. Everyone else will get defeated by computers, but not the best few human beings. There's something special about them, which was just objectively false. The computers just kept getting better at a pretty steady rate. And so the famous match between Deep Blue and Garry Kasparov, in which Deep Blue won, it was 1997. For 5 years, there was this interesting activity where the best humans in the world would play the computer on roughly equal terms. But 2005 was the last time any human being ever sat down from a computer, across from a computer, say as powerful as my laptop, and beat it, or even drew against it. It's simply, they are now just, and they kept getting better, right? They were on a growth curve, and that was not, the world kind of lost track of what was happening, but they just kept getting better, better, better. Okay. We could also express this in terms of numerical ratings. You could think of like amateur chess players, people who play chess as a hobby. Most of their ratings range between the numbers 1,000 and 2,000, right? Numerical rating, higher is better. A player who's 2,000 is a very, very good amateur chess player. And then, by the time you get to like 2,400, 2,500, your friends are saying, have you considered playing this professionally? 2,800 is the best player in the world. And current chess engines are well beyond 3,300. It's actually hard to evaluate ratings up there. It's probably like 3,600, somewhere around there. Right, so they are, and differences are kind of translate and variant. So 3,600 to 2,800, they're as far beyond the best humans as the best humans are beyond like amateurs who are pretty good and play on weekends, right? That's how far beyond they've gotten. Okay, so the question is, this is an activity where again, if the goal was to win chess games, computers are far, far beyond us. So what happened, right? It's fair to ask, can we derive any stylized facts from observing chess? Now, obviously, every domain is different, right? Chess is not the same as mathematics, it's not the same as medicine. First of all, it's a game. People do it for fun. But it certainly has some of the characteristics. And so here are some stylized facts that I think are sort of interesting to keep in mind. 4 of them. So 1, chess as an activity is as popular as ever, actually more popular than ever. That's because of some other features of the internet, such as live streaming of chess games on Twitch and YouTube, the availability of enormous amounts of online play. You can find people to play with all around the world on sites like Lichess. Now, we could ask, other activities might not remain as popular as ever when AI becomes superhuman because we don't particularly enjoy doing them and we're happy to delegate to algorithms. Chess is something we enjoy. But it was not the end of chess when algorithms became superhuman. A second point, which I think is actually showing up in many domains where AI is beginning to surpass or match people, this principle that the spectators now know as much as the participants, right? So, this kind of democratization of expertise, if you want to call it that, where somebody watching with a chess engine turned on suddenly knows as much as the expert sitting at the chessboard. So much so that things have been dramatically inverted, right? So in 1980, if say, or 1985, Kasparov sits down across from Karpov in a world championship match, they're playing. Afterwards, there's a press conference. They play for 6 hours. They play a game. They come out, and there's a press conference, and the chess journalists all ask them, why did you make that move on move 25? And they explain, because the 2 people in the world who understand this game that just happened the best are Karpov and Kasparov. They understand it way better than anybody else in the audience. And so they're here to share their wisdom with people. Fast forward 40 years to 2025, people playing the world championship. First of all, they're sitting in a sort of soundproof booth to prevent cheating because people are watching with engines turned on. And everyone's watching with the engine turned on. And they're watching the board. And they're wondering, why is this person not playing pawn to g5? It obviously wins. Because the engine told them that. And they're sort of forgetting that if they didn't have the engine on, this would be not at all obvious to them. And they wouldn't even see this. And so the fact that they're kind of yelling at their TV, effectively, wondering why this chess grandmaster is not playing pawn to g5, it's not nearly as easy as it looks when you have the engine turned on. But it also means that when the players come out for their press conference, and you can watch chess press conferences, this is actually what happens, they ask the journalist, what should I have done on move 25? Because the 2 players who understand the game the least are the 2 players at the board. Everybody else was watching with the engine turned on, right? There's been a complete inversion of the expertise. And I think that's sort of an important thing to keep in mind as we look at these other activities. A third one, the aesthetic standard. So I'll talk about some research I did beginning with Ashton Anderson in around 2015, coming back to look at chess through this lens. And I had played chess a little bit in high school, and I came back and I looked at it in 2015. And one thing that struck me, and I read a bunch of stuff where other people had this reaction, that in the 1960s, 70s, 80s, all of classical chess, the aesthetics of the position were a proxy for safety, right? It was very hard to calculate chess positions, and you didn't have a chess engine to tell you what the right answer was. So you fell back on sort of aesthetic heuristics, along with calculation. Rooks, and again, knowledge of chess, not crucial, but there were certain principles that apply. Each sport has its own principles, and in chess there are things like rooks belong on open files, knights should be on advanced outposts, don't double your pawns, all this stuff, right? You come back in 2015, and the board just looks ugly. It just looks, it's a mess, right? Pieces are everywhere. It's sort of like if 1970s and 80s chess was this sort of elegant, sort of cinematic sword fighting scene, 2015 is more like a kind of fight with broken beer bottles, right? It's it's ugly. Because what happened, they practice with chess engines, and they know that if it works, it works. It doesn't matter if it looks good. They're just going tactically. They're going by the calculation the engine showed them. Of course, the more you see it, the more its own aesthetic emerges, right? It's not that there was no aesthetic. It's just that the aesthetic had changed dramatically because we now had engines to help calculate. And again, think about your favorite domain where you're worried that AI might be sort of competing with humans. There again is this issue that the human aesthetic standard we've often had has both been because we value aesthetics, but also because we often use it as a heuristic to guide our work. And those heuristics start to erode when AI becomes superhuman. Finally, something which I'll come back to in much more detail, the AI frequently sets you up to fail. Right? The fact that you're looking at the engine going, how can these people not see that pawn g5 is obviously winning, goes away when you turn off the engine. Suddenly you're lost, right? Okay, so around 2015, it was occurring to me that, like, we have this genuine bona fide superhuman activity going on with AI. Let's study it in various ways. And so I convinced Ashton Anderson, a longtime collaborator of mine, that we should look at this. And then we joined forces with Siddhartha Sen at Microsoft Research. Ashton admitted a student, Reid McIlroy-Young, who did a bunch of really exciting development on this. And one question that we asked was, okay, we have engines that can make amazing chess moves in order to win chess games. But can we also learn to match human decisions? Right? Because we might want to set up model systems where superhuman AI interacts with human capabilities. But if I want to, for example, run a billion iterations of something, humans don't really have the patience to sit through a billion iterations playing a superhuman AI. So I need a stand-in for the human part of it. And so it's natural to want to train something that plays like a human. And so the goal was simply a prediction problem. Given a position P encountered by a human player of rating X, predict the move the player will make. Right? I would like to build something that as faithfully as possible makes moves like a 1500 rated chess player would do. And so we did this. We built a chess engine called Maia. And the idea was, by then DeepMind had released Alpha 0, which had taught itself to play chess just from the rules and through self-play. The open source community had replicated it because DeepMind didn't release Alpha 0, but they built this thing called Leela, which was basically an open source version of Alpha 0 that also taught itself through self-play, also became superhuman. And the head of that neural net was trying to make good chess moves. So if you take off the head of that neural net and you put on a head that tries to, as faithfully as possible, make the move that the human 1500 rated player made in the training data, then you have a predictor of human moves. And so you could make a Maia for each rating, 1100, 1300, 1500, so forth. And each one basically is sort of best at predicting for the rating it was tuned to, right? Maia 1100 peaks in its performance at 1100, Maia 1300 peaks in its performance at 1300, and so forth, right? These are the performance curves of how well it does at matching moves of people of each rating. And they're much better than the sort of leading engines, both Leela, the neural net engine, and the leading traditional engine, Stockfish. Right, so if you actually train to do this, then you can do much better. Because, of course, right, the alternative is I could take a superhuman chess engine and just sort of dial down its search all the way until it's basically making random moves. And by some sort of intermediate value theorem, if I go from superhuman to making random moves, somewhere in between, you will play it on even terms. But that doesn't mean it's playing like you. It just means you win about as often as you lose. And in fact, it's not playing like you, right? You have to actually train something to actually play like you. Okay, and so the point is, you can do a bunch of things with an engine like Maia. We've actually been experimenting with it for sort of teaching purposes, for example, right? It can, for each rating, try to guess what a human of that rating would make. So again, this is the most chess-like thing. It's not important if you actually follow what's going on in this position. But the point is, if you ask an engine like Stockfish, the most powerful traditional search chess engine, what to do, it'll say play pawn takes a6. And Maia predicts that around 1500 is when a player will start playing that. Whereas at lower ratings, it'll play the much, much weaker move, pawn to b6. Okay? And so it'll actually try to find the point at which you cross over from one move to another as the rating goes up. All right, so we released this on Lichess. It turned out to become very popular. As it turned out, we released it right at the start of the COVID pandemic. People were online playing huge amounts of chess. By now, it's played several million games. Some interesting things, actually. So the most played version is Maia 1100. It plays like an 1100 rated thing. We turned it on in a mode where it always made the most likely move. Right? So there were sort of two choices when you release Maia onto the internet. You could either have it draw from the distribution, right? It's computing a distribution over moves that 1100 rated players play. There's this probability in this move, this probability in this move, this probability in that move. It could either draw from that distribution, or it could just pick the most likely move. It turned out, after some experimentation, people seemed to enjoy it more if we picked the most likely move. But a funny thing happened, which was its rating on Lichess was actually around 1400, not 1100. Right? It's trying as hard as it can to play like an 1100 rated player. That's where it has the best move matching accuracy. And when it actually plays games, it plays at 1400. And it's an interesting question exactly why this is. We have a conjecture that we certainly believe in, which is that 1100 rated players often lose chess games, right? A chess game goes on a very long time and one bad move can throw it away. And those bad moves are often idiosyncratic mistakes that they normally wouldn't make. Right? So it sort of suggests that if you're rated 1100 and you could succeed in always playing the move that you were most likely to play, you would actually gain 300 rating points just like that. Right? You don't actually need to get, you just need to avoid the kind of rare mistake. You can make all your typical mistakes, just concede those, but avoid the rare mistakes. Right? This effect goes away around Maia 1900. Maia 1900 is rated about 1900, and so whatever gain there was seems to be at this lower end. Okay, some other things that happened once we released this. So first of all, we can only create Maias up to about 1900, 2000, because there just wasn't enough training data for us beyond that to try matching. And the problem is that if you start doing like actual chess engine search, it gets too good. But subsequent work, there's continued to be improvements all the way up to the present, has actually managed to produce really good move matching accuracy, so this new system called ALI, up to say 2700, 2800 to play like the best players in the world. We also started to create personalized bots, right? So the algorithms that you train using AI conceptually exist on this spectrum, ranging from kind of the world we are in, say, with large language models, where there's a very small number of models that produce most of the output, right? Because it's just so hard to produce big models, we just get very few of them, right? Like, almost everybody uses one of a few large language models on the internet. So we have a kind of algorithmic monoculture where we're getting the same decisions. Even though there are, in principle, presumably many ways to build something with that performance, we simply don't have the money, or the capital resources to produce that many different models, so we produce a few. All the way ranging to increasing algorithmic diversity as we go this way, maybe at the other extreme to what we might call mimetic models, which are actually matched to your behavior, right? If I have enough data about you, I could fine tune the model to play like you, or to write like you, or to do any of these other activities like you, right? So that's at the other end. And we began to produce these mimetic chess models. People began to ask us like, wait, so if you can do that, you could actually produce like personal, or maybe with ALI, you could produce personalized models of the best players in the world, right? So we could finally find out what would happen if this famous player had played this famous player, even though they never actually met in real life, right? So people came to us and said, for example, Bobby Fischer, the world champion, the world champion, this is a little too AI focused. The world champion from 1972, 1975, the only player from the US to become world champion, famously abdicated his title without ever defending it in 1975 and never played chess again. And he would have played Anatoly Karpov, who at the time was a young Soviet grandmaster who then became world champion for a long time. And everyone wanted to know what would have happened if they met. And so people approached us and said, well, you can finally find out. Create a Fischer bot and a Karpov bot by fine-tuning and have them play each other. And we tried to explain that's not really how this works. Like, that might be interesting, but it would not tell us what would have happened in the counterfactual in 1975 if they had actually played each other for all sorts of reasons. And it's sort of a reminder that like, when we build mimetic models, we often ascribe behaviors to them, even though that's not really like appropriate. Now you'd say, okay, that's obviously silly. People would never really make those mistakes in real life, ascribing, to a mimetic model of somebody, behavior that, trying to ascribe to a person behavior that was only made by their mimetic model, right? Would that really ever happen? I want to argue, though, that has happened for a long time, long before AI, for example. So, for example, right, when do we see cases of people ascribing behavior to a person that was only ever done by their mimetic model? Well, in a non-AI context, here's one of many examples. This is someone named Mark Felt. You may or may not recognize him. Mark Felt was during the Watergate scandal that brought down the presidency of US President Richard Nixon. Mark Felt was Bob Woodward and Carl Bernstein's inside source. Bob Woodward and Bernstein wrote for the Washington Post. They wrote a series of articles that broke the Watergate scandal. And their inside source in the administration was someone they referred to only by a pseudonym, Deep Throat. And they promised never to reveal who that was. And shortly before the death of this inside source, he decided he wanted to reveal who he was to the world. And he said, I was their source. My name is Mark Felt. I was an official in the Nixon administration. And they admitted, and they said, okay, now that he's revealed himself, we can say, yes, it is true, that is who it was. And so in his obituaries a couple of years later, many of the obituaries said, as he famously told Woodward and Bernstein, follow the money. That was the famous quote from the Watergate era. Follow the money, because if you want to unravel the scandal, you have to figure out who paid whom and trace out the path that the money followed, and that will trace it back to the source. Okay, follow the money. About a week after these obituaries appeared, there was another op-ed written by William Goldman, the novelist and screenplay writer, author of the screenplay for The Princess Bride, and author of the novel The Princess Bride, and many other things. And he wrote in his op-ed, it's funny to read these obituaries because Mark Felt never said follow the money. I said follow the money. Because I wrote the screenplay for a movie called All the President's Men, which was a movie version of the Watergate scandal. And in that, I wanted to summarize the whole mass of articles that they had written, and I wanted to distill it down to a pithy phrase, and so I created this phrase, follow the money. I wrote that. And so in some sense, the most famous thing Mark Felt ever said, right, the only quote from him that ever appeared in his obituary was said by his mimetic model created by William Goldman. So I think these things are harder to avoid than you might imagine. And I think they're only going to get sort of more present as we keep going. I wanted to talk about this fourth stylized point, which is the AI frequently sets you up to fail, right? You're watching the chess game with the engine turned on, and it looks easy. But if you turn the engine off, suddenly it's not so easy. Similarly, we have many examples of sudden handoffs from AI to human. So for example, you use the AI to write code, and it writes a bunch of code. You don't really understand how it works, but it seems to be working. And then your boss wants you to explain the code. And the AI is not there to help you explain it. Now you have to explain it, right? As people often think about with handoffs in cyber-physical systems, you're driving in a self-driving car which is doing some maneuver using the laws of Newtonian mechanics, and it goes offline, and suddenly control returns to you. If it's doing something that feels human-like, you can take over. If it's doing something really complicated, it's an open question whether you can take over, right? Recent example, many people have recently told me, and you've probably heard similar stories, that people say, one thing I love using ChatGPT for is that my landlord hasn't come to fix my dishwasher, and they're really supposed to, and I need to write them a polite but firm email saying, you haven't come, I really need you to do this, and that's really awkward, I don't like doing that, so I got ChatGPT to do it. Which is great, except the next thing that happens is your landlord calls you on the phone and wants to talk to you about your polite but firm email, and now it's you on the phone, not ChatGPT. So AI is constantly putting you in these situations. Now, apparently humans worry about these things, or have worried about these things for a long time. Just to take two examples from fiction of sudden handoffs from powerful AI. So on the left we have a scene from The Fellowship of the Ring. This is the aforementioned Fellowship of the Ring. And they've just decided to embark on the admittedly dangerous plan of marching directly into Mordor, the heart of enemy territory, to destroy the Ring of Power. They all look a little nervous, but they're like, it's okay because we have Gandalf, the all-powerful wizard, with us. And so it's all going to work out okay. And now, sorry about any spoilers, but if you read ahead, about a couple chapters later, Gandalf falls into a giant chasm and is not seen for another book and a half, leaving the rest of the Fellowship to embark on this super dangerous plan all by themselves without the all-powerful person who has suddenly handed it off to them. Similarly, this is a scene from the movie The Wizard of Oz. From left to right, or right to left, this is Glinda, the Good Witch of the North, Dorothy, and the Wicked Witch of the West. And roughly speaking, Glinda has just convinced Dorothy to take an unusually aggressive negotiating position with the Wicked Witch of the West. And Dorothy obviously looks terrified. It's like, that's okay, because Glinda's here to protect me. And of course, if you've seen the movie, Glinda vanishes about a minute and a half later for literally the entire rest of the movie, leaving Dorothy to fend for herself. So apparently, we've for a long time been worried about powerful entities embarking on a plan with us only to leave us to actually carry it out. And so we thought we could actually do a version of this with chess. Could we build a version of AI which has two properties that are in tension with each other? One is that it's superhuman, but the other is that it does not set us up to fail, or at least does it as little as possible. So here's the experimental setup that we tried. And so this is, again, with the four of us. So Ashton and me, Sid Sen, Reid McIlroy-Young, and now this is with Karim Hamade, who is another student of Ashton's. Imagine the following four-player chess version of chess. And again, knowledge of chess is not crucial. Think of any two-player board game. So Leela, the all-powerful superhuman AI, is going to play as a team with a human, and another Leela human team is going to play over here. They're going to take turns making moves for white. This team will take turns making moves for black. They do not communicate with each other. Okay? Leela makes the first move, human the second move, Leela third move, human the fourth move. Don't communicate. Okay? And same thing has happened on the other side. Of course, the problem is Leela doesn't know it's doing this. Leela's just making the best chess move it can. So on move 25, Leela sees this amazing rook sacrifice that's going to launch a winning kingside attack as long as you play out the moves correctly. And so it sacrifices the rook. And on the black side, they take the rook. And now it comes back, but now it's the human's turn to move, and they can't communicate. The human has no idea how to follow up this brilliant rook sacrifice. So they play something, which of course is not the right move. And now this team is just losing. They're just down a rook for no reason. Right? So Leela has unintentionally set up the human to fail. That's exactly the kind of scenario we've been talking about. I could do this with Leela and Maia, because if we want to actually experiment with this, it's fun to try this with humans for a few games, but eventually we have to actually swap Maia in. And so we have a Leela Maia team. And so the question is, could we do better than Leela on a team like this, right? Could we create, say, a partner bot that through self-play is actually better at playing as a team with Maia? Still no communication, but we're just going to train the partner bot through self-play to do as well as possible. So it doesn't quite know what's going on or why its good moves sometimes don't work out. It just gets a reward signal that as often as possible, it's supposed to be beating this Leela Maia team under these conditions, okay? And when you do this, what you sort of hope happens is indeed what happens. So 3 possible partners for Maia: Leela, the partner bot, or just another copy of Maia. And when they're teamed up with Maia against a Leela Maia team, well, obviously, if it's Leela on the team, then it's symmetric. It's Leela Maia versus Leela Maia, so it's half-half. The partner bot actually wins 2/3 of the time against the Leela Maia team, right? So it really is better as a partner for Maia. When I say wins, we're counting draws as a half point, wins as 1 point. Maia plus Maia actually wins about 1/15 of the time against Leela Maia, which is kind of amazing because Leela is superhuman. So that's just a sign of how frequently Leela is completely shooting its team in the foot when it plays. And in solo competition, obviously by symmetry, that's 0.5. The partner bot versus Maia, right? Maia never beats Leela, like really never. The partner bot actually wins about 1/7 of the time, which does mean it's superhuman, right? Because humans cannot beat Leela basically ever. So we have this thing which is superhuman, but kind of a medium level of superhuman. It's weaker than Leela, but much better as a partner, right? So it's exactly the kind of thing you'd want. And it's a kind of way of creating a form of safety through comprehensibility, right? The moves are comprehensible, and therefore it's safer to play with this thing as a partner, even though it's weaker in every other sense. All right. Let me talk about some of the models that these and later AI systems are using, okay? So obviously, the chess engine we've been talking about right now use an explicit model of the world, right? They actually have an internal chessboard because we built it in. And that's maybe the simplest kind of world model. We built one in directly. But obviously, when we're working with large language models or transformers, we're talking about a pure sequence generation model, right? We interact with it. It's trained on data. It just outputs a sequence of tokens to try to maximize some likelihood of that sequence of tokens. So when you play a game against that kind of a model, no one built in a chessboard or some other game board in there. It just learned through training data to output sequences that are plausible for this particular task, such as playing chess games or anything else. So now the question is, if I look at this, could I actually extract, right? If I just watch its sequences, could I find some way to extract a state of the board? Is there even one? Right? Is this large language model that only knows how to output sequences, does it somehow, somewhere in there, have some implicit internal representation? Right? It's a question we can ask about many kinds of systems when we ask about world models, right? Does a fly buzzing around this room, going into different corners, have somewhere, right? Could I extract out of its neurons a map of the room, or is it simply reactive and simply bouncing off of things? We were sort of inspired in this by some earlier work by a group at Google that was doing this for the game Othello. Knowledge of Othello is also not required for this talk. And they were trying to extract the state of the game board. And we asked, OK, let's ask this for the chess context also, and for other things. So the first worry, of course, is what do I mean by the state of the board, right? Like this thing simply learned to output moves and to play this game, from the training data. It doesn't know about rooks or knights or bishops. Maybe it does have a representation, but that representation is so different from chess that I wouldn't recognize it, right? Is that possible, right? Is it possible that it actually plays chess totally correctly? It just has never heard of a rook or a bishop. And not only that, but it doesn't even know about, sort of hard to picture. I don't know how to give you an example of that for chess, but I do know how to give you an example of that in general. So here's a different example. Here's a much simpler game. Let's call it a number choosing game, okay? We're going to take turns choosing numbers from the set 1 through 9 without replacement, okay? And we're each trying to get 3 numbers that add up to 15. That's the game. So for example, I pick 2, you pick 5, I pick 8, you pick 4, I pick 6. Now actually you're in trouble because if I pick 1, I add up to 15. But also if I pick 7, then 7 plus 6 plus 2 is 15. So in some sense I now have 2 ways to win. You can only block one of them, you block the 7, and I pick 1, and I win. Okay? Sample play of this game. Take turns picking numbers, try to add up to 15. Okay? Right. Okay, and so we could, for each sequence of moves, we could say, is this a valid play of the game? Does it lead to a win, a loss, a tie, a draw? We could try to develop strategies for playing this game. You'd be like, okay, Do you think you'd be good at playing this game? Is it tricky? How hard is this game? Let me suggest a way you might try to play this game. What you could do is arrange the numbers in the following pattern. What's useful about this pattern? This pattern has the property that every row and every column and every diagonal of 3 adds up to 15, and nothing else adds up to 15. So under this rearrangement, the new description of the game is try to pick items so that you get 3 in a row, a column, or a diagonal. It is tic-tac-toe. Right? So it's not that this game is reminiscent of tic-tac-toe. This game is tic-tac-toe. It is identical to tic-tac-toe. And so this is, of course, the problem with trying to impose a sort of superficial notion of world model on top of what the sequence generation model is doing. Because an algorithm that learned to play this game, if we then said, I wonder if it's really learned tic-tac-toe, let's ask whether it knows there's an X in the upper left corner, it could justifiably, because it only knows this, could justifiably ask, what's an X, what upper left corner? It doesn't know about that representation. It has learned a totally different representation. So it says that at some level, we can't impose our own notion of state, our a priori notion of state. We have to induce the state directly from the sequences. This thing really is a black box that's just a sequence generating machine. And so to ask what is its model of the world is going to have to go directly from the states, from the sequences to the states, right? So far we've gone from states to sequences. I give you some board states, we move through them. Now I have to go the other way. Here's a way you can actually go the other way. So we have sequences, right? Let's say that if I have a given sequence, right, a given play of this game, I can try to extend it to a full game. And I can either do that in a valid way or an invalid way. Let's say 2 sequences, let's call them sigma and tau, are equivalent if for every possible suffix I put after it, sigma followed by rho, every possible suffix rho, sigma followed by rho is valid if and only if tau followed by rho is valid. Okay, so these 2 sequences are basically equivalent if everything completes one versus the other. So for example, in the tic-tac-toe context, A1 upper left followed by B2 center followed by C3 lower right versus C3 lower right, B2 center, A1 upper left are equivalent. Right? We see that because we get the same board state. But under my definition, they're equivalent because anything I stick afterwards behaves the same. Right? Once these two, right? That's sort of what state is. State is a big collection basin for a bunch of sequences that are all kind of act the same. So that's the proposal. If I just have a sequence generating machine, I could think of a state as just a bundle of sequences, maybe a lot of them, that all behave the same way when I stick things onto them. Right? That's what's happening here. This board state is all the sequences that lead to it. Now, if this evokes, if you were at some point in your life a CS major and this evokes faint memories, that's because this is called the Myhill-Nerode theorem. Right? The Myhill-Nerode theorem says that if I'm just working at the level of sequences, I could say the set of valid sequences is recognizable by a finite state machine if and only if this set of equivalence classes is finite. And I can actually build a finite automaton for a finite state machine for this collection of valid strings, this language, by using these equivalence classes as the states and using transitions between them. Okay, so a state is a bundle of sequences that all behave equivalently. So what we did, and this is in some work with Keyon Vafa, Justin Chen, Sendhil Mullainathan, and Ashesh Rambachan, we used this Myhill-Nerode methodology to go test large transformers that have been trained to do certain sequence generation tasks, right? Based on this principle that, say we know, so we could do this for game playing, we could also do this for, say, driving directions, right? We train a transformer to give driving directions in Manhattan, right? So we train it on just a sequence of these things. And then we look at, has it learned some kind of map of Manhattan? But of course, the problem is we can't just impose our map of Manhattan. We have to figure out what it really did. And so this idea of states as bundles of sequences, right? Say it's all driving directions starting from 8th and 13th in Manhattan, right? And I want to know, does it know about the idea of like the corner of 44th and 5th? The set of all directions that get you from 8th and 13th to 44th and 5th, and there are many such driving directions, is a giant bundle of sequences that is in some sense is the state 44th and 5th. Right? That whole bundle of driving directions is 44th and 5th. And so that's how you can try to reconstruct a map of Manhattan. In the same way, that's how you can try to reconstruct chessboards or anything else where you're moving through some finite collection of states, possibly a very large collection of finite states. And the sort of rough takeaway here is that when you do this, you discover that the actual models they have when you try to build this are internally quite inconsistent with each other, right? That they're very good at giving, they somehow are achieving this balancing act of giving good driving directions most of the time, and yet when you actually push them, they don't actually have a consistent state representation, right? I think this notion of world model is actually quite interesting. I've been talking about for these very stylized systems, you know, Othello or chess or tic-tac-toe, driving directions. We can do this for constraint satisfaction problems or logic puzzles. But probably more broadly, it's going to be interesting to ask about world models in much more qualitative contexts, right? So for example, if we were to write a story, the story we write, as we wrote it, we would presumably have in our head some kind of a world model, right? So, you know, LLMs are pretty good at writing stories, even LLMs simple enough that I can run them on the command line on this laptop, you know, such as Llama 3.2 here. I can say, write a 2-paragraph scene in which 2 college students have just finished an intramural soccer game, which their team qualified for the campus-wide intramural finals. They are the last 2 people left in the field. It grows dark, and they have a conversation. And it writes this story about Emily and Jack, and Emily let out a sigh of relief. You know, she asked Jack, "Can you believe it?" Her voice laced with excitement. Jack stopped and grinned. "I know, we killed it out there." And you know, the 2 friends have been playing on the same team for what felt like an eternity. This was the first time making it to the final. The stadium scoreboard was changing the game stats for the next day's matchup. You know, Emily is nervous about tomorrow. Jack chuckled, "We've got this, Em," because you know Jack, he's always so confident. You know, and it's just spitting out words. It's just saying words, right? And so a person writing this, we would have a sort of theory of mind of the person who wrote this. We would picture that they had in their mind Emily and Jack standing on the empty field, sort of like this AI-generated image. And, you know, and they're talking to each other. And, you know, and they kind of know that Emily and Jack, because a narrative like this has an enormous amount of latent state that we just read off the text, right? The internal emotional state of the characters, the state of the relationships, they play on the same team for eternity. The stats on the scoreboard are changing. They're getting ready for the next day's matchup. There's a ton of internal state. And so there's this interesting question, which I would claim is actually still fairly open. When an LLM writes a story like this, how much state did it really have as it spat out those words? Ranging all the way from it was literally just stringing one word after another to it somewhere in there you could extract all that stuff. And I think that's sort of an interesting, you know, it's a question that we still really don't understand very well. You know, in the same way we don't understand it for images, right? Because that's sort of the point. It's not that we could add, you know, the question like what's just beyond the edge of this picture in this AI-generated image is not well defined, right? There is nothing beyond the edge of that picture. This is just a bunch of pixels. Now, there are other fields where a sort of qualitative level advance actually happened because people finally did the enormous amount of hard work to build real world models. One example is computer graphics in a project led by my Cornell colleague, Steve Marchner. Let's go back into Mordor one more time. This is Gollum from the movie version of Return of the King. And Gollum in those movies, and this is now a long time ago, so you can take my word for it if you weren't around, was sort of a breakthrough in putting computer graphics characters side by side with human characters in movies, because it sort of looked natural. It didn't look like you would just draw a cartoon character into the middle of the frame. And that took an enormous amount, right? It's like one of those magic tricks that's actually much, much harder to do than it looks, because Steve Marchner led this project in which they spent years in a darkened, you know, in a dark room with lighting sources and measuring the detailed reflectance properties of human hair and human skin. Because the problem had been that when you tried putting a graphics character in a movie, the skin was wrong and the hair was wrong, very subtly. But as humans, right, this is the principle of the uncanny valley from computer graphics, we react viscerally to that. Right? If the skin is wrong and the hair is wrong, it looks vaguely zombie-like, and we just can't get past that. And so you needed to get over that hump, and that needed a huge amount of physical modeling of the world, right? So this hand-drawn picture is very different from this one, because this is based on extremely detailed physics. And the question is, you know, do we need that sort of thing in the kind of AI models that we build? I think that's very much a kind of open question. So this is, you know, all part of the search for this thin part of the hourglass, right? The abstraction barrier that is going to lead us, you know, to sort of create AI that maybe is going to be more adaptable to building these applications on, right? What is the right abstraction barrier that we can actually work with? And I think this is an ongoing activity. There are a lot of interesting sort of both practical problems, a lot of interesting theoretical questions, right? These kind of state extraction questions, these Myhill-Nerode methodologies, these search for state spaces implicit in sequence generation models is certainly one big category of them. To suggest one other line of work, we could actually also ask, like, a lot of this has been about the process of generating language itself, right? We see a bunch of training data come by, and we try generating sequences from it. And we try generating valid words from this language, valid strings from this language. And this is a very old question in learning theory. In fact, it's in some sense one of the very oldest questions in learning theory. It goes back to some work about 60 years ago by a researcher named Mark Gold, who said, if we abstract the language generation problem all the way down to its essence, we could think of language learning as a kind of game played between nature and a learner, or in the language of theoretical computer science, between an adversary and an algorithm. The algorithm would like to learn the language, and the adversary would like to make things as hard as possible so the algorithm might fail. So for example, we could picture in this stylized form, the adversary thinks of a secret language, call it K, that comes from one of a countable list of alternatives. Okay, L1, L2, L3. It's one of those, and we don't know which one it is. And the adversary utters the strings of K one by one, right? It says strings of K. And the goal of identification is that the algorithm is trying to guess which language it is. Now, in 1967, Mark Gold was motivated by, not just computers, this is 1967, so there weren't really big data sets, but also actually by infant language learning, right? A 6-month-old is learning a lot of language, but they're pre-verbal. So they're listening to their parents speak their native language. The parents tend to speak only positive examples from the language, right? The parents, sure, there are a couple of grammatical stumbles, but they're not speaking gibberish. They're speaking positive examples. And the infant can't really ask, is my guess correct, because they can't verbalize. But somehow that infant becomes a fluent toddler, somehow, right? And this was a puzzle to Mark Gold and then to Dana Engelman, who followed up on this in 1979, because the theoretical results here were negative, right? Except in extremely restricted cases, it's impossible in this game for the algorithm to win. It's simply, there are just too many choices. It's only heard a finite number of strings. How could it guess out of this infinite list of possibilities the correct language? But language generation is a little different. What's interesting here is this was always a question about language identification. You have to actually learn the language. But that's not really what's happening, right? The 6-month-old who becomes a fluent 5-year-old can now speak fluently in their native language, but they can't litigate edge cases of the grammar of their native language. In the same way that if you learn to program in Python, right, you could become a fairly competent Python programmer, but if you go to a super hard coding interview and they ask you, would this nested double null pointer dereference compile successfully, you might not know the answer, because you don't know the exact specification of the version of Python you're using, you just know how to program in it. Right, so generating strings is actually different from identifying the language. To generate, you just have to pick a big subset in the middle and safely generate from that. So we went back to this question in some joint work with Sendhil Mullainathan, and we said, what if we went back to Mark Gold's 60-year-old language learning game and just changed one little thing? We said the algorithm no longer has to guess the language. It just has to, every time, output a new string from the language, right? Something that's not yet in the training data, right? Because that's what these models are doing. They see a bunch of language, and then in return, they say new things that you recognize as valid utterances from the language. And it turns out this problem, even in this extremely stylized theoretical, right, this is the entire theoretical model we're talking about, is much, much more tractable. Now, for every collection of candidate languages, there's an algorithm, right? There's an algorithm that will win this game, right? It will watch a finite number of strings go by, and after a finite number of steps, it will output things that are always valid in this language, right? Okay, so a big difference between generation and identification, and a sort of hint in this very stylized model that maybe there is something more to be said here about generation, even if we leave behind the hard learning questions that it had seemed to entail. And so with that, I'll wrap up. Right, the point is these last 10 years, right, this AI revolution, we've been interacting online with a rapidly growing ecosystem of these very, very powerful algorithms, right? In some cases, we have these sort of monolithic things creating a monoculture of a very small number of models. And in some cases, we create many, many of them, right? We even adapt them to our individual behaviors. There's a lot of these sort of stylized facts, which I think we discovered from looking at first at chess, now at some of these other domains. both the kind of empowerment of spectators, right, that we all now are experts because we have the engine running, the change in aesthetics, and finally, the way in which the AI can set you up to fail unless you're careful, and the goal of building safer AI that does not set you up to fail, right, that can actually work directly with you. And finally, I think a lot of really interesting theoretical questions in this idea of like, what is the model of the world that this AI system has inside it, right? Ultimately, it's just a black box that is exchanging sequences with you. And somehow from that, we're going to have to use theoretical tools to try building up some of the elaborate infrastructure that it presumably has implicitly going on. And so I think this is a real sort of crossroads of a lot of fascinating theoretical questions with a lot of implications both technically and for society more broadly. Exactly the kind of activity I think that the Simons Institute specializes in so well, bringing together people to talk about these kinds of questions. And I really appreciate the opportunity to discuss them all with you. Thanks very much.
Thank you very much, John, for the fascinating, really thought-provoking talk. We have time for questions. So raise your hand. I'll try to bring the mic to you so even the recording will catch your question.
Thank you. I want to go back to your paired chess playing, Leela and Maia. And I think you used the word comprehensible then. And my question has to do with, suppose we swap another engine in there, will the more comprehensible symbiote do well against with some other engine? And in particular, a human dropped in, will that trade-off work more well? And will it use features like control of center and broken pawns as part of what it means to be comprehensive?
Yes, these are all great questions, right? So the question is like, I said comprehensible, which was, a deliberate choice here that Maia should know how to follow up on this. And so I think this is a question that we're still exploring. So I don't have a definitive answer. I think both things appear to be true. So it is certainly, it's trained through self-play with Maia. And so the number one thing it is it's comprehensible to Maia. And so think like, doubles tennis or 2-on-2 basketball, like your partner that you've practiced with, you do things that are comprehensible to them, and it may not be comprehensible to a generic human who gets swapped in their place. So I think that's definitely important. There's some other things with more time I could mention, like the partner bot also gets good at creating things that are hard for the opposing Maia, actually, right? And so it's also kind of aiming, like in the spirit of 2-on-2 basketball, it's like, it's like trying to go around the weaker player on the other team. We have looked qualitatively, we've asked sort of annotators to look qualitatively at the positions. And certainly the moves that, like the partner bot appears to make fewer sort of engine moves, right? So if you listen to chess commentary, the two grandmasters will be studying a position and the engine says that white is winning and they can't figure it out, and then they go peek at the engine to figure out why that is. They say, oh, that's an engine move. Like, we would never have found that. And so in some sense, the goal of the partner bot is, one way to ask the question is, can you play at a superhuman level and never make, quote, engine moves? And from sort of qualitative looking at it, it certainly seems to make fewer of those kinds of moves, but a sort of deeper analysis is still something we're pursuing. Yeah, thanks.
Any other questions?
Yeah, thanks for a very interesting talk. My question is, do you anticipate that AI will ever become superhuman at mathematics, thereby putting you out of a job? And if so, how is that possible given the fact that basically AI is just working on training data and you're actually asking it to do something that's outside the training data?
Yeah, all great questions. Yeah, so right, is math going to eventually put me out of a job? And how would that be possible since it's only trained on the things we've already done? Yeah, so I think each of these domains is interesting in its own way, right? So, I think if we're talking about like, if I were up here as a composer of music, which I certainly am not, right, then, it's only been trained on the music humans have written. How does it go out of that? Mathematics has this interesting kind of duality in that it's a human activity that we do as humans, but it also follows well-defined rules, right? And so, in the end, math is a game of pushing symbols according to a certain logical set of rules. You write down, these are the axioms, these are the rules you're allowed to do to transform written sets of symbols. These are the inference rules. And what David Hilbert told us, circa 1900, is that in the end, math is just a gigantic tree, and we start with what we know, and we apply every possible rule in every possible way, and we fill out this tree, and that consists of every theorem that could ever be proved, right? So math at some level is a static object. It has rules just like chess does. It has a search tree just like chess does. It's an incredibly big, incredibly wide search tree. It has decidability problems that chess does not have. And so there are a bunch of things going on with math that are not going on in chess. But there's a sense in which at some level, something that was omnisciently powerful at computing, you would argue, is just going to start filling out this tree. Now, there's a second, of course, meaning of math, which is it's also a human activity. We are trying to advance each other's understanding of mathematics. And so, if this thing were to, say, accomplish some task that, we, desperately would like, say, proving a, size 10 times n circuit lower bound for an explicit, function in polynomial time, then we would say, okay, that's an amazing result. But maybe the proof is 500 pages long, and each page is sort of this dense thing that we can't even understand half a page of, and we have to get through 500 pages of it. And so in some sense, like, what would we have learned from, to what extent is this contributing to mathematical research? And so I think that there's actually a fascinating paper that you can read on this human dimension of mathematics, and sort of what this all means, written in 1990 by Bill Thurston, the Fields medalist, which is actually partly autobiographical, actually partly about his time here at Berkeley, but in which he argues that in the end, because we know math is ultimately mechanizable, ultimately it's just this giant search tree, that's not what the field of mathematics is. The field of mathematics is about the advancing of the human understanding of mathematics, and he, I think, develops that argument very, very well. And I think it's all the more, it was a prescient thing to have written in 1990, but it's really all the more acute, I think, right now.
Hi, John. Yeah, that was a great talk, by the way. So there's we've heard a lot recently about AGI and when will we achieve it, etc. But there's a different question that I'd like to ask which is, given all that's happening now, when do you think we'll reach the level where we have a superhuman understanding of what humans are, of human abilities, intelligence, and how we think?
Yeah, no, I think it's a great question. First of all, like all these questions, I find it so hard to look beyond the next 2 months as to what's going on, just because things are changing so rapidly. I somehow feel deep down, although I cannot prove, that people who are very confident about what the world will look like 2 or 3 years out might well be wrong. I mean, I think that's been my working assumption. It's just things are changing too rapidly. We can't know what's ahead of us. But having said that, yeah, I think it's a very important kind of question. I mean, a lot of what I think we've been doing here, sort of as often as we've been turning the AI or the machine learning model at the ground truth, equally often we've been turning it at the human decision maker. Because I think it's equally interesting to ask, let's try to build a model of what the human is actually doing. And I think those are kind of comparably important questions. And both for, I think, the sort of deep reasons that I think you're getting at, which is ultimately, I think a lot of our fascination is trying to understand what our experience as humans. I mean, I think I would additionally say that I think when we say there's this fascinating mystery which is intelligence, I think we often mean the fascinating mystery is also the subjective experience of being human, because lots of things are intelligent, and a spider building a web is intelligent, and it's fascinating to ask how that happens, but it's a very different question from the subjective experience of being human, which I think is a question all unto itself, which in some sense AI may be able to help illuminate, and certainly where areas like the humanities, and large parts of social sciences are going to be very, very important for this. And of course, in a purely instrumental sense, an AI that can understand humans are presumably going to be better at working with humans, as some of these experiments are suggesting. So, yeah.
I have 3 hands up. Go in order. Awesome.
Thanks for the amazing talk. I had a quick question about the thing you mentioned with given a number of static strings, can an AI actually produce a novel phrase?
Yeah.
And I'm curious to know what you think about Latin as well as hieroglyphics, and how the role of maybe the bias of number theory might play a role.
I mean, yeah, so I think what's interesting is each language that we're talking about comes with its own particular constraints. And so I think, one thing that's going to be interesting sort of across each of these different languages is, they sort of differ in the sort of variability that we have. First of all, they differ in the encoding, they differ in the variability, and I think all of those are going to affect this. So, a sort of very abstract result like the one I put here says that in some sense, in the limit, right, there's an algorithm which in the limit is going to arrive at sort of generating new strings. But it's going to do that at very different speeds for different languages. So it sort of pushes us into a quantitative question that it's certainly possible that there are some languages that are much quicker to learn or much quicker to converge to than others. And I think that's a very interesting direction.
So I'd like to actually pick up on exactly this point here and also connect it with Umesh's question. So there's this thesis in psychology that children who are learning to read learn more effectively when they're simultaneously learning to write. And you see this particularly in teaching children Chinese, right, where they have them write the characters 100 times as just a repeated exercise, right? And so this synthesis becomes an intrinsic part of recognition.
Yep.
And I think that's part of what you're seeing here, which sort of suggests that this kind of phenomenon is giving us some hints actually about humans, and that we can learn about humans from this, observing these kinds of phenomena.
Yeah, no, I think like this whole area of like grounded learning, in which I sort of learn abstract symbols by reference to grounded objects, and I can thereby do some kind of alignment between them, is a very promising direction. I think we are learning that humans that's effective for humans. I think we're also learning that that's something about the process of learning itself, right? I think like there's something about the act of learning when you have two parallel streams of input that potentially makes it more efficient. And I think humans are very effective at picking up on that, absolutely.
Just a quick comment on his question. If you actually use the very popular song recognition engines out there that obviously scan Spotify and all of that, right?
Yeah.
When you presented a version of the song that is live or a cover, meaning not the original artist, slightly different tone and stuff, it will always fail. And then I asked ChatGPT, why is that the case? It's because there's other human learning mechanisms in place, such as emotion, which I know that song. How come you can't figure it out? I keep banging the engine. Anyway, to my question, this is more on a curiosity relative to famous points in chess history. Would a mimetic version of your engine mimicking Bobby Fischer, the young Bobby Fischer, and his opponent at that time for the very famous queen sacrifice move, will it do the same thing? For the non-chess playing folks, the queen is the most powerful piece on your side, on either side of the board. For him to sacrifice that so many moves, leading to eventual checkmate of his, or meaning the loss of his opponent on the match, that was my highlight game when I was learning chess way back when. I was wondering if the engine would mimic that and thereby establish itself in chess history for the second time.
Yeah, it's a great question. So we actually, at this point, it's still a struggle, and those of us trying to build bots representing these famous players from chess history, we're still some distance from being able to produce bots at that level. Like, at this point, we can produce fairly accurate bots for people, say, with about 2,000 games they played, ratings between 1,000 and 2,000. To the extent you can actually do stylometry on this, right? You can actually sort of figure out which of these candidates played this game. At the grandmaster level, though, it remains very difficult. But for that particular chess game, I think one of the striking things in the history of chess engines was, again, in this late 80s, early 90s period, people felt like there were certain of these moves that were just flashes of human genius. And it was sort of striking when in the early 90s, engines began finding all these famous moves from chess history, right? You'd feed in the position and it would find it. And I think that was sort of one of the early signs that the end is coming, right? That these things really are going to surpass humans. And that happened maybe like 5 to 7 years out from the eventual sort of defeating of a world champion. Because of course, in order to defeat the world champion, you have to not just find the individual brilliant moves, you have to actually string them together and not make mistakes over the course of a whole chess game, and that took a few more years. But yeah, that definitely was an important moment in the history of chess engines.
This is maybe picking up a little bit on the question of learning with respect to chess, but perhaps expanding it to other areas of endeavor. Have there been efforts in determining how good an automatic tutor can be in improving human performance? And what are the metrics there? without exhausting the 2T in the process.
Yeah, this is right. So the potential of this for human tutoring. So this is something we've been looking at a lot, and it's been a hard problem. And actually, some follow-up work has been trying to pursue this also. Like this feels like a very natural domain for teaching, and it's a challenge because. One thing is that improvement at chess is difficult, right? Like most people can play thousands of games, and if they're not systematic about it, they just won't improve. And so it does need something more active. One thing we've been looking at is sort of the sort of cross product of like say Leela and Maia, right? So I have a position, and I take every legal move in that position, and each one has a value according to Leela, how good a move it is, and each one has a value according to Maia, which is how likely it is that you'll make that move. Okay. Now imagine a scatter plot. I'm going to plot all those points in the plane. Okay, so on the first axis is Leela, and the second axis is Maia. So if you think about the upper right, Leela thinks it's good, and Maia thinks you're likely to play it. That's good news. Those moves are things you're likely to find, and they're good moves. Right? The lower right is Leela thinks that it's a good move, and you're unlikely to play it. Those are like the hard moves, the moves you're unlikely to find. Upper left, Leela thinks it's a terrible move, and Maia thinks you're very likely to play it. So one argument for sort of tutoring is like, look in the upper left, right? These are your frequent kinds of mistakes. And to the extent you can learn to recognize those. And so it's actually been quite interesting to sort of play through a game that you've played and look at all the legal moves laid out in the Leela-Maia plane. And sometimes you're playing from the upper right. You're playing good moves that you're likely to find. And sometimes you're playing from the upper left, and those are often the things to look at. So I think these are the kinds of like sort of basic sort of the substrate for these kinds of tutoring activities. But it's a big open question, sort of how to use these most effectively. Yeah.
Can you extrapolate to mathematics?
Great question, right. I mean, it's fascinating to think about, like, if I had a model of you doing math research, then, we could potentially say, like, this is a trick you were likely to have missed. This is one you were likely to have found. I don't quite, it feels like it's hard to even imagine the training data. Also, one of the things about chess is all the steps are instrumented, right? Like, we see all the moves. In math, we see your paper, we see the steps you wrote, but of course you wrote those long after the fact, right? We haven't instrumented the process by which you thought about it. So a natural follow-up to your question is like, if we really had a thing that was good at AI math, and someone really wanted to use it to get better, should they also try to create a system that instruments their process of working things out so that they can actually sort of watch the steps and try to figure out which ones,
Yes. So I was thinking about the difference between our models of the world and AI models of the world, and what really brought it home to me was your example of the number game, where you have to add to 15, and how that is equivalent to tic-tac-toe. But that if the number game is implemented in AI, there's nowhere a tic-tac-toe board. There's no. But in our mind, my model of tic-tac-toe is a spatial model.
Yeah.
So I wonder if there's something generalizable about that our human models of the world tend to be often spatial, because we are navigating creatures, but AI models never have to navigate.
Yeah, it's a great question. Like, it does feel like as humans, because I mean, one thing I think about with large language models is the idea of like tool use, right? We're trying to train them to recognize when to use a built-in tool, and it does. And obviously I lack the neuroscience expertise to say anything, but it's clear that like we have certain cognitive tools at our disposal that we use more easily than others, including spatial reasoning. And so we have a kind of tool use of our own, and tic-tac-toe feels more natural here. There's a beautiful example, coincidentally, involving chess that the AI researcher David McAllister created in the 1980s, which was, he said, consider, for those of you who know how a king moves on a chessboard, any adjacent square, and how a knight moves on a chessboard, two squares one way and one square the other. It's a true fact. Okay, so it's a true fact that a king on an empty chessboard can reach every square. Just kind of walks that square. It's also a true fact that a knight on an empty chessboard can reach every square. That's much less obvious. It has to kind of like keep doing these L shapes and get around to the. So one of those is. It's so obvious you don't even know, like, it's just so obvious. And the other one, you really have to kind of, is that really true? And both of them have problems in the corner. The knight gets stuck in the corner, but the king gets stuck in the corner, right? The king in the corner only has a couple options, but that doesn't really pose you any mental cognitive problems. Now, for those of you who think about like graph algorithms, reachability graphs, both of these are statements about the connectivity of a 64-node graph of degree 8. So to an algorithm running graph connectivity, these are just they're different graphs, not isomorphic, but they're both 64-node graphs of max degree 8. they're comparably hard. But to humans, they're just worlds different. One is super hard, one isn't. And that somehow is because one activates this kind of spatial reasoning instinct we have, and the other one just totally fails to. And so I think, yeah, there's a lot going on there that I think is very, very interesting.
Maybe I'll ask one question on in terms of models of the world. I guess we have this mental model of whatever field of math we are in, and that enables us to ask questions. And for example, the beautiful question you asked on language generation as opposed to thing. What's the, there's a lot of talk on AI for math, but what about asking questions and abstracting questions which are not very crisply defined?
Yes. Yeah, I think, and that actually is another thing. So if we go back to like Bill Thurston on proof and progress in mathematics, math is a human activity, yeah, I think that's a key thing to think about. Like this sort of David Hilbert-like tree of all possible theorems where I just start with the axioms, I just start grinding out every possible rule of deduction, and I get to all theorems. Right, the activity you're talking about is such a basic mathematical activity, which is like creating like a definition or creating like a lemma, which sort of takes, I don't know what, like a path, a subtree, some piece of mathematics and creates, again, an abstraction layer. And now, back to the point about cognitive tools, if I can really internalize this definition, it now becomes an atomic unit that I can deploy, even though to actually expand that would be an enormous amount of work. And so like actually like in Hartley Rogers' sort of classic book on recursion theory, he makes this nice point about like definitions are, we struggle with quantifier alternation. And if we can find the right definition, we can collapse layers of quantifier alternation so we can keep it in our heads and then sort of work from there. And so, yeah, I think that's an activity that, it sort of comes back to an interesting thing, which is we like this for two distinct reasons, which gets back to the aesthetics versus utility, right? So if I go back to like stylized fact number 3 here, the aesthetic standard, we love beautiful definitions for two reasons. They're beautiful and they help us do math. And the problem is it's not clear the AI needs them to do math. And it might not recognize that they're beautiful. And so this might be exactly the same as coming back to chess and seeing how ugly it is, that the AI doing math just might not need them. And we're going to lose some of that elegance that we really appreciate. So I think it's a very interesting question of like what's going to happen there.
Well, we're almost at 7 o'clock, so let's thank John again for.
Thanks very much.
Thanks, John, and thanks to all of you for making it out here, which makes the event all the more special. Thanks.
I'm around, yeah. It's just that Will is visiting, so. Imagine like every. How should we walk through the forward?